Okay, so I think we start. Full screen again. I only forget the shortcut because it's so hard to remember. It's
full screen.
Yeah. Okay. So it's so high, right? No.
No.
It's full screen. Okay, I see. Great. So thank you for inviting me. So I'm going to present the SMC-based simulation for conditional diffusion models. So this paper has been out for like a few months ago, and I don't know if you read it yet. But it's a very, the language in which it is written is very specific to biology and protein and so on. So it does not look very accessible, but the underlying idea is very interesting, and there are a lot of open questions regarding this. So that's why I decided to present this today. So here's an outline of the presentation. So first, I quick review of general diffusion-based generative models. So some of you work on that, some of you don't work on that. So I try to make it accessible to everyone. We start the unconditional case and the conditional case. Then we can talk about the replacement method. And one of the contributions of the article is that they try to show why the replacement method introduce a bias that cannot vanish even if you have a large neural network. And then the authors present their SMC-diff method. So it's a method that uses SMC to guide your observations toward the observation that you want to condition on. All right. And then we will try to interpret this SMC-diff method by looking at it dependent on dimension. And we also show that the SMC-diff method can be seen as an SMC sampler, but with a suboptimal backward kernel. And the last part, which is actually the main purpose of the paper, is to show some application to protein generation. And then I will finish with some future directions and references. Right. Okay, so the idea of denoising diffusions is that you have some data, you diffuse the observed data into noise, and then you learn the backward distributions so that you get a generative model for the observed data. So here I'm presenting a very simplified case because I'm trying to go fast for this part. So you have a distribution like dxt, rxt, dt plus the square root of 2 dwt. Then you can have the reverse distribution as the reverse process, which is also a diffusion, and you can write its drift term and its noise in the formula above. So let's say I pick a discretization step delta, and then I say xt, which is not in bone, which is equal to xt delta, where xt is in bone. So let's say that fx equal to x. So I'm taking a very simple example where you have the xt tends in distribution to n01 as t tends to infinity. All right. So the idea is that I will simulate x0, x1, xt according to the forward diffusion for some large t, and then I model the backward dynamics according to this. So at the end, xt follows a n01 distribution, n0 id distribution, and then xt given xt plus 1 is modelized by a normal distribution where the gradient here has been replaced by a neural network. All right. So there are many ways you can train this. For example, the most simple way that you can do, the simplest way you can do the maximum likelihood. You have initial data x01n and diffuse data xt1 minus tan t. Then you can write the log likelihood with respect to delta, with respect to theta, which is written there. So you have is here the xt plus 1, the drift term, and the neural network part. And so there is also an alternative view for the individual terms, so that you can see why this is consistent. So you're trying to estimate the gradient, which is the best function that minimize this expectation. So it's the best representation of the log gradient of p xt plus 1 given xt in terms of the function of xt plus 1. And we have this because of the Fisher identity that I show here, which allows you to express the log gradient of vt plus 1. In some ways, it allows you to, it's kind of a marginalization formula for xt plus 1 with respect to xt. All right. So now we look at the conditional case. So in the conditional case, you do more or less the same thing, but the goal is different. So the goal is different because you have observations x0 n equal to 1 to n, and you want a generative model for x0 given y0 equal to y0 star. So you would like to consider the dynamic, but here's this time the dynamic has changed because you keep y0 constant all the time. So if you do this for t large enough, then it is easy to sample from xt y0 given y0 star because they are approximately independent. So it remains to learn the inverse dynamics. And again, well, what you can do, so here is yt, sorry for that. I have completed this slide last night, so there are quite some errors on it. So your forward distribution is described by this equation, and then your backward diffusion will be more or less like before, except that yt doesn't change, and you have the gradient here, which is the gradient of xt given yt, and then it's a gradient with respect to x, but otherwise everything is more or less in the same vein of idea as before. And so again, this is more or less a mere repetition of what I have said before. So you got xt, you modelize it according to a neural network S theta, where you have xt is n0 id, yt follows your data distribution, and xt follows the backward dynamic, and yt is kept the same during all the process. You can again write, so here should be a theta. You can write the log likelihood of each of the step, which takes this form. Well, I know that in reality, people usually take the bridge between x0 and xt, but I'm doing this for simplicity here. All right, so an alternative view of this again is that you can say that you try to estimate a gradient, which can be written as an integral, a conditional expectation in terms of Fisher identity. And so your neural network solves this minimization problem, which is the best approximation of the function gradient log p xt plus 1 given xt minus phi xt plus 1 y0. So the best approximation of this using xt plus 1 and 0 and y0. Okay, so I hope that if you do not work on diffusion models, then at least you have some very basic ideas of this. So I try to present a very vast field on 4 slides. So I know that is a little bit rapid here. Right, so the replacement method. Okay, so suppose that as before, now you have realizations of z0, x0, and y0. However, you also want to condition to answer coordinate of z0, so not necessary results of y0. For instance, you can say that, okay, you have x0 in R2, y0 in R2. So you have z0, which is a 4-dimensional vector. And you wish, besides a generative model for x0 given y0, you also want a generative model for let's say Z02, Z03, given Z01, Z04. Okay. So if you had fitted a model for the conditional distribution of xt y0 given xt plus 1 y0. So if you have applied the method that I mentioned before, well, we could not use it again to model the conditional distribution with respect to other coordinates. Okay. So the question is, what if I had learned the joint model? So I add noise to Z0 as a whole. I have Z0, Z1, and Zt. And I have already fitted P theta of Zt given Zt plus 1. And can I reuse this information to condition with respect to an, arbitrary coordinate that I may not know even when I start to learn my model?
Maybe I can give an example, which is the in-painting problem. So basically, you want to in-paint some images, but the zone you want to in-paint is completely different from one image to another. So you don't want to have a right-time a conditional score just for a very specific, in-painting problem. You want to have it so that it's valid for any problem.
Yeah. Okay, so so there is one idea for this that has been already presented in the literature. So it's more or less natural, right? Okay, so you have Zt is equal to Xt Yt. So for now, we will assume that P theta captures the P Zt given Zt plus 1 perfectly. Okay. And so so if you have like a perfect modelization by a neural network, well, no, I mean, what's happening here, if you look at the model, the graphical model on the top of the page, you see that because you are adding noise independently to Zt, to X0 and Y0, what happens is that once you are given X0 and Y0, then your two processes, Xt and Yt, are independent. So one of the key property here is that the probability of Xt given Yij is just equal to the probability of Xt given Yi for all I are smaller than j. So in the previous algorithm, you have Y0, which is fixed. So at each time t, you have Yt equal to Y0 star, and then it is propagated back to time 0 automatically. You have nothing to do. So now you need to modify the generative model somehow so that you gradually bend the sequence Yt, Y1, Y0 back to Y0 star at the endpoint. Right. So in the literature, the replacement method has been proposed. And what people do is the following. So here I put two equivalent versions of it. So the version on the left is the more common one, but they are both equivalent. Okay. So your input is a diffusion model Z0, Z1, Zt, with trained backward kernel P theta Zt given Zt plus 1. So first, you are going to sample from the Y following the forward distribution. So you get Y1T star. Then you start from the end, you have Xt, follow a normal distribution 0, 1. And then for each t going from t minus 1 back to 0, you sample Xt tilde by the conditional distribution of Xt given Xt plus 1 and Yt plus 1 star. And this distribution, you can sample from it because you have learned it through the parameter theta here. All right. So another way to describe that, which is completely equivalent, but it's more intuitive, is that, okay, first you sample Yt star given Pyt given Y0 star. Then you sample Xt tilde at the end for the normal distribution. And then for each step t, you sample at the same time Y small t star and Xt, where Yt follow the distribution of Yt given Yt plus 1 and Y0. You can do this because it's just a Markov chain. kind of a Brownian bridge, and then XD term, which follows the backward distribution, again, the one that you have learned. Okay, so the output of this is X0 term, and people say that, okay, it's approximately P X0 Y0 star distributed. Well, this claim is of course not correct. So in the paper, they have shown that, well, I mean, you can show it yourself. It's very easy to see that why it's not correct. So the target distribution that you want to simulate is the distribution of X0T, Y1T, given Y0 star, right? So that distribution can be decomposed by the independent property, by the spectrum property of this kind of model, as Py1T given Y0 star, and then Px0T given Y0 star. And so for the first term, you keep it the same. The second term, you make a backward decomposition in a Markovian way. Right. So now for the replacement method, the law that you are sampling from is completely different. So at first, you sample a trajectory Y1T as before. You sample from HT, but then at each time you replace the YT with the YT that you have obtained before, and you do not take Y0 into account. So what's happening is that even by naked eyes, let's say by naked eyes, you can already see that the two distribution is not the same, and you can have a more formal statement by using the chain rule for KR divergence. Yeah. So do you have no? Okay. Okay. So this is very basic calculus. So the chain rule for KR divergence, you can, well, people usually learn it for two distributions, for distribution of two variables, but actually it's valid for 3 or 4 variables as well. So we have two distributions Q and M, and you can decompose the KL progressively in this function. And there is a short way to write it. You can say that is KL of Q with respect to M on dx, and then Q of dy given x with respect to M of dy given x, and so on. So this kind of formula is very practical to treat a difference between two Markov chains like this. Okay, and if you apply this kind of stuff, then you immediately get that the distribution, I mean the KR divergence between the distribution that you get by using the replacement method and the target distribution B is a non-trivial sum that is not 0. All right. So in the paper, if you look at the appendix, then the author also provides explicit calculations of these terms for Gaussian distributions. So I don't show it here. You can look at the paper. Those are just Gaussian calculations, which are a little bit tedious. But the main message is that this thing is not 0 and can be really non-trivial to understand. All right. So now we look at the SMC-diff method and the method that the author have presented. Okay. So who worked with the sequential Monte Carlo methods here? Who are familiar? Okay. So not many people, right? Okay, so replacement method tries to bend a Y T back to Y0 star, but it does so in the wrong way. So modifying a Markov process gradually is exactly what SMC methods are for. So if you know how to simulate a Markov process, mu t dxt mt minus 1. Okay, so I will not read all the notations aloud. This is just a Markov process going from xt to x0. Okay, and now you want to sample from a modified version of it. So if you look at the measure here and the measure there, then the only difference is that you have these additional terms, gs xs plus 1xs. Okay, so you modify gradually a macro process, and the way that sequential Monte Carlo methods work is very natural. So I'm trying to summarize something in 3 lines. So here, first you simulate n particles, xt minus 1n, n equal to 1, and from 1 to big N, to capital N, and they are all IID according to the measure, to the Markov measure of xt and xt minus 1. Okay, so this you can do because you know how to simulate the Markov process. Okay, and what you are trying to do next is you are going to take into account gt minus 1. So you are going to take into account the additional term here. So how to do that? Well, it's very natural. You will calculate its value at each of the particle. So you said you said omega n equal to gt minus 1, xtn, xt minus 1n. And then you normalize this weight so that their sum is equal to 1. So now you have an approximation of mu t dxt mt minus 1 xc dst minus 1 times gt xt minus 1 xt. Okay, I'm sorry, there should be a gt here, but I think you get the idea. Is that here you have an approximation of this, and then you reweight them according to the weight of gt minus 1, and so at the end you get a weighted approximation of the distribution times the function gt. Okay, so now you have a weighted system. This is not good for reasons that I will not detail here. So what you are going to do is you are going to create a new unweighted system where all the weights are equal to 1 divided by n by resampling from your weight distribution. Okay, and then okay, so now you from time t you go to time t minus 1, and you know how to go to time t minus 2, and so on and so forth. Okay, so that's the essential sequential Monte Carlo method. So let's come back to SMCD. So again, I'm assuming that my neural network learned perfectly the distribution. I'm sorry. So first I proceed as I have done before. So I simulate y1t star given y0 star by the forward dynamic. Okay, and then to sample from p x0t given y0t star, which is what I want, I notice that okay, that the distribution is proportional to the joint, and that joint I can decompose it backward. So I start from xt given yt star. So here is just the backward decomposition of this. Okay, you start from time capital T, then you go to time capital T minus 1, capital T minus 2, and at each time you condition with the latest observation. So now you have a Markov measure that you can simulate. Is this one the measure that I'm sorry, the measure that the first 2 terms here is the Markov measures you can simulate. As when I say that exactly the framework of this slide, I mean that you have a distribution of this form where you have a Markov part and a weight term. Okay, a potential function. Sometimes they also say that a potential function. So you have the Markov part here that you can simulate easily, and you have the potential function here, which says how much yt star matches xt plus 1 and yt plus 1 star. And this is something that you have learned before from your neural net. So one funny thing here is that the base Markov measure, if you look at this is exactly what you do in the replacement algorithm. And another interesting thing is that the normalizing constant. Okay, I didn't talk anything about the normalizing constant here, but let me say that in sequential Monte Carlo, there is a quantity that you can estimate, which is called the normalizing constant. And the normalizing constant of this SMC algorithm is a py0t star divided by pyt star. So pyt star you can calculate it easily because it's at the end, so it's more or less a normal distribution. And the py0t star you can decompose it starting from py0, and then you add in the Markov stuff. And so this allows you to derive an estimate of py0. Okay, so this is the density of the model, so the density of the data at time 0. I don't know whether this estimation is very precise or not. We have to try it. Okay, so now I'll talk about something that is not in the article, but is interesting to know. Because what is happening with these guys of model is that the way that you diffuse x0 and y0 independently create a state space model with a very specific structure. And so at each time t, your SMC algorithm sample from pxt given yt or small t capital T star, but in fact it is just sampling from pxt given yt star. Sorry. So what you are doing is that, okay, you have pyxt given yt star, you extend it into pxt minus 1 xt given yt star, and then you reweight it to get pxt minus 1 xt given yt minus 1 star. And the performance of SMC algorithms depend on something called effective sample size. So who have heard of effective sample size? Okay, there's more people. Great. So effective sample size is related to the chi-square divergence between the two last distributions. And if you calculate this chi-square divergence, and it simplifies to just the distribution of xt minus 1 given yt minus 1 star and xt minus 1 given yt star. So there is one thing that you can show quite easily, is that if you take any f divergence d, which includes chi-square divergence, chi-square divergence, or Kuhn-Labor, and so on, then you can show that this stuff is bounded by the divergence between y0 given yt minus 1 star and y0 given yt star. And in particular, really striking here is that the bound does not depend on the dimension of x. And you can also show that it is tight in the sense that if you consider the supremum over all possible distribution of x0 and y0, then the supremum of the left-hand side equals the right-hand side. Okay, I think I will just give you intuition because I am very lazy to write down the full proof of this stuff, especially for the inequalities tight part. It's easy, but it's just tedious and very long to write. Anyway, so the intuition is very simple, is that yt minus 1 and yt can only transfer information to xt minus 1 via the bottleneck y0. Okay, so if you look at this, you can see that you try, so the difference between these two is just the way how yt minus 1 and yt transfers their difference to xt minus 1, and there is no way to do so except to go through x0, and that's why you have a bound here. You can prove that using data compression inequality and this kind of stuff. And by picking an appropriate x0, you can also show that the bound is tight. Okay, so I'm going to go through that. Okay, now I'll talk about another interpretation of SMC leaf method. So you can see it as an SMC sampler, but with a suboptimal backward kernel. So who knows SMC samplers? All right. It's okay. So anyway, so yeah, I'm trying to continue. So at the time t, you have pi t xt, which is equal to p of xt given to yt star. So what is quite surprising, and I haven't realized this for quite a long time, is that actually you can calculate exactly the ratio between pi t xt and pi t plus 1 xt plus 1. So, okay, I won't go into the detail of the derivation, but again, it is a consequence of the model. So the main message here is that the ratio between two successive distributions can be calculated. It depends on, so the term you have here is the backward decomposition. So you can calculate it using the neural network that you have studied. Here is the forward one. And this term, you do not need to know it because it does not depend on xt or xt plus 1. Okay, so if you know SMT samplers, you know that you can now sample from pt xt using SMT sampler with any backward kernel, kt xt plus 1 given xt. Well, normally, well, this thing is forward in time, but because we are sampling backwards, so it's a backward kernel. So, so this is your target distribution. Okay, so you start from pt plus 1 xt plus 1. And then you try to propose xt and then reword it somehow so that you get this term in final. And then you get the cancellation, you see the cancellation here. And at the end, you get the distribution that you want here. All right, so there's another result that I won't spend time to prove because it's tedious algebraically. But SMCD boils down to choosing this backward kernel to be the forward kernel of the distribution pxt plus 1 given xt, which is clearly very suboptimal. Why it is suboptimal? Because the goal of that kernel is to bring pt close to pt plus 1. But there is no reason to bridge xt yt star and xt plus 1 yt plus 1 star by adding just some noise to xt. Okay, so I think that there is surely a much better kernel to work with this SMT sampler that will provide a superior performance to the method that they showed here. All right, so time for some applications to protein. So I'm not an expert. I'm not an expert in protein and this kind of stuff. Is there anyone here who comes from the protein group at all? Okay, thank you. Great. So if I say something wrong, then please forgive me and try to correct me on that. But I mean, I try to understand the best that I can using the article. So there are 20 amino acids in total. And let A be the set of them. And a protein is an element of S, an element S that is in A to the power of N, where N is the length of the protein or the number of residues. Okay. And the N coordinates are divided into the motif coordinates M and the scaffold coordinates S, such that the union of the two sets is 1 to N. Okay. So you have N coordinates and you try to divide them. And why do we think about this kind of divisions? Well, because the motif part is a part that is supposed to confer biological functions for making enzymes and vaccines and so on. So for the protein, there exists a function Fn that turns each sequence S into a 3D structure. So we have a sequence with the amino acids. You can apply a function to get essentially n points in R3. Okay, so you turn a sequence into a 3D structure, and this 3D structure, I will denote by R, and this so-called the backbone structure is a central object here. So if you just want to look at the problem in a mathematical way, then you can say that okay. All I am interested in is this variable R, which can be decomposed into two parts, RS and RM. And my goal is, given a motif, can I sample the corresponding scaffolds? So the two-London Reed version of this is that according to distribution, I mean, I just want to sample from RS given RM, R scaffold given R motif. When I have a sample of proteins that follow more or less the distribution of the backbone in the nature. Okay. Right. So how do the authors train and evaluate the data? So I'm going quite rapid on this because I have skipped a lot of details, but in the article they have described all of this carefully, and I think that is one of their main contribution. So apart from the SMC part, which is also novel, the other contribution, the other big contribution to the article is that they design neural networks that are very adapted to modeling proteins. So the raw distribution is learned over a set of proteins from the protein data bank. I mean, there's no choice. If you really want to learn the distribution of proteins in nature, then either you collect yourself or you go to the data bank to do it. And so, well, in the previous slide, I have said that, okay, we model the joy, this is not a joy conditional. Yes, we model the joy conditional P of RT given RT plus 1 via neural network, right? So with a Gaussian distribution where the drift term is described in terms of neural network. But in the case of proteins, the network structure have to be optimized to take into account some specific structure of the protein, such as the PRT is invariant with respect to on the rotations. So it is on the rotations in R3. And then here you have some kind of sequential properties of protein where the distance between two adjacent coordinates tend to be small if I is close to J. Right. Okay, and then this is the funny part, the way that they evaluate their conditional simulation. So when they have RM star, they are going to sample from RS given RM star using something like, okay, SMCD or replacement method or whatever. And then they sample 8 new motifs are tuned the M18 given RS. So that now they take, okay, sorry. Now they take the RS that they sampled before using the algorithm. They resample again new RM using existing protein tool. So what I want to say here is that it is a very challenging problem in protein study to sample from to sample scaffolds given motifs, but it is easy, it is very easy to sample motifs given scaffolds because you have tools to do that. Okay, so let's resample that, and the performance is reported as the maximum of the norm 2 distance between R star and R2 MI minus RM star. So I don't know what you think about this. I have a lot of doubts over this kind of evaluation, but well, I do not have any better idea, to be frank. So yes, that's a quantum kind of try to evaluate it. And so in their experiment, the dimension of the motif is fixed, so around 15 and 25 residues. So that is between R45, R75, and the experiment seek effects of an increase in the scaffold dimension. All right, so here's what they have got. So just to explain things clearly, so let's only look at the left side, okay, because the main message is more or less the same for the two examples. So on the left side, on the x-axis, you have the scaffold size in terms of residues. So if you think about the conditional simulation that we have mentioned before, then it is to say that the number of dimension here is more or less this number times 3. Okay, so here's the number, the dimension of x. All right, and then the dimension of y is fixed as before, as I have said before. So and on the y axis, what they show is their evaluation criterion. So the closer the numbers approach this line, the better. And they compare 3 sampling methods. So the SMCD that we have described, the replacement method that we have described. What's the fixed one? Well, the fixed one, well, in the replacement method and the SMCD, what you do is that you diffuse Y0 to get Y1, Y2, and so on. And in the fixed method, you do not diffuse, but you keep Y0 the same. Okay. So what we see here is that, okay, the SMCD method seems to perform better than the replacement method, and the replacement method perform better than the fixed one, which is easy to explain because in the fixed one you keep Y0 all the time. So Y0, I mean, when the time t is big, you do not have how to say it, you do not learn the gradient in the region of Y0 anymore. So your gradient evaluation is not very good. And that's why the fixed method has a bad sampling efficiency. All right. But what is quite disappointing here is that you see that when the dimensions of ice increase, there is a degradation in the performance of SMCD. Whereas we have shown before that theoretically, if the neural network is perfect, then SMCD performance must not depend on dimension. So I think the problem here is obviously when the dimension increases, you have problem learning the gradient with the neural network, and we have not been able to quantify that, and that's why this degradation in performance happens here. All right, and so there is still a lot of open problem because as you can see, whenever the scaffold size exceeds about 100, then you have no methods that can work for the moment. All right, so
the fixed one is the best one for like 1999.
in the first example, the fixed one is the best one for
like the largest scaffold size.
Yes, but I mean, if you look at the confidence interval of this, you see that the 3 box plots are more or less, I mean, overlap a lot, and you cannot say that. I mean, in this region, everything breaks down. To be sure. Okay, so some future directions and some reference. So the most urgent problem now is to improve the performance of this stuff, because if you look at this, you see that when the dimensions increase, there is a problem that may be related to neural network that we do not really control, do not know how to control theoretically. And I also talk about performance because I have said about the suboptimal proposals that we can surely improve somehow. And there are also other things that I will not mention here, but I think the performance of this algorithm SMCD in practice really needs to be improved somehow, and we need to find a way to do that. Then another direction is to extend this to other kind of diffusions with more complicated structure. For example, when you have applied Schrodinger bridge on it, or when you use implicit model and so on. So the theoretical guarantees is also something missing, because for the moment I have said, I mean, I have repeated multiple times that we assume that the neural network learns perfectly the backward dynamic, which is never the case. And because it's never the case, well, we do not have precise error quantification as the error quantifications that we have in this article, the Bartoliano. Even in these articles, I assume that the neural network is at most m, when you have a number m, and you say that the neural network approximates the gradient with an error, with a uniform error of m, almost surely, which is a strong assumption, but still they have shown something. Whereas in the case of conditional stuff, for the moment we have no theorem yet. And so there is no continuous time framework. There is also another thing that I want to look at is about the stability of particle filter. So because well, you do not work on SMC, so I will not talk more about particle filter on this. So if you have any other ideas, then welcome, because I've been working on this for about 1 month, and I've been really interested in continuing the direction. Okay, so some further references for this. Well, you have classical reference for diffusion model, references for conditional simulations, and reference for sequential Monte Carlo methods. All right, so thank you for your attention.
If you look at, have you played a bit like, so you have this bond on the effective central side, on chi-square divergence.
Yeah.
Can you get back to it?
Yeah, yes, of course.
So somewhere here, this what you get on the right is just related, well, it's related also to the distribution of y naught to start with, but also the speed at which you diffuse between you know, yt minus 1 and yt. So I mean, doesn't it mean that you could basically kind of get a control of this quantity by playing the speed at which you diffuse the yt?
Yes, yes, of course you can play with the speed that you.
Because you expect that the beginning is going to be tough. You should really add really just a bit of noise, not to have this quantity to kind of.
Yes, but the main question is what is the complexity of the algorithm in general?
Yeah, no, sure. After that, I agree,
but
but at least you could try to have some control on the chi-square.
Yeah. So one thing I haven't said about this is that I have tried numerically this bound, and I've tried numerically to calculate the ENS between stuff. And what I observe is that it is very unstable. I mean, the fact is that yt minus 1 and yt are random quantities because you simulate them from diffusion.
Sure.
And what you see is that they can vary a lot. And if you look at the box plot of the ENS sample size, then sometimes you have a very high and sometimes you go very low actually. So I think that diffusing yt may not be the best option. Maybe we should try to find some more stable way to find yt star actually. But yeah.
People try to just kind of learn a family of networks or models that kind of can perform denoising on like an arbitrary condition set by varying it during training, and then like typing over like all possible kind of permutations of your sampling and then your conditioning on.
Okay, so what you say is that you can learn a model that can denoise arbitrarily by.
So like say in the image in painting example, training by like randomly sampling in painting bits, and then having one model that like for any kind of in painting region can diffuse on that.
Yes, I haven't thought about that.
I think it's has been done. So basically for in painting, they just do a lot of random regions. So basically it's not even like one region, you can have multiple regions that are missing, and then one network. So the input will be the image with a lot of parts missing, and then so that will be fed into as the input, and so there will be no noise in the conditioning. But that's for fixed images. So maybe the size of the image is fixed, but then there will be random blur or like random shapes in that image, but the total size is the same. So I don't think it's.
So in this problem, like the actual dimension of the motif and scaffold can vary. If you add the dimensions together, they might not be quite similar. But
yeah, that's why you need to learn a lot of things. I think from this problem, a lot of missing.
Okay, so do you have any question over the chat? Maybe.
Check. There's no questions. from the chat.
Okay, great. So Sophia,
Is that-
okay.